We left off with Gibbs free energy, our dear friend delta G. And I'm going to remind you, chapter 7 is a bit of a beast of a chapter. There were 6 big concepts, and we've hit 3 so far: enthalpy, entropy, and delta G. And now we have pieced those things together to see how overall we can answer this question of how do we know if a reaction is going to happen from an energy standpoint? How do we know if something is energetically favorable? And the reason this is important, and the reason honestly it relates to health sciences, many of you are going to go into careers where you are studying the body or taking care of the body or coming up with plans to feed the body for the rest of your life, whatever you choose to do. And therefore, you need to understand how the body thinks. The body's not going to do anything that's not energetically favorable. Okay. Now, there are times where it needs help, okay, to speed up a reaction or things like that. But our body makes millions of these decisions. Obviously, it's amazing to me when I think about how complex the body is. And we have to sit here and do all this math. The body doesn't have to do that. It's just like it inherently knows, right? Anyways, let's pick up with this slide right here. Here's our equation for delta G. Okay, remember that delta G equals delta H minus T delta S. And we're just going to do a couple more practice problems to refresh you and to remind you how to go about these things. And some of what we talk about here, these first few slides, are going to help directly with a few homework questions, which I'm going to give a shameless plug on the homework. Do not procrastinate that homework. I've already gotten several emails about how to answer certain problems on the homework. And from very diligent students, I will say, students that are like, hey, I'm trying to knock this out. And it's not all that easy. And I'm not trying to scare you. I'm just saying, don't wait, so that if you need to email me and ask me questions, I'm available to help with that. Okay, so let's look at this reaction. We have calcium carbonate, and this is a solid, and it is decomposing into calcium oxide gas and carbon dioxide gas as well. And we're given the delta G. The delta G is a positive 31 kcal per mole at this temperature. Okay, which means at different temperatures it would be different, but at this specific temperature, here's the value. So the first question is this reaction spontaneous at 25 degrees Celsius? I need to pull the chat up, because some of you might type the answer. What do y'all think? Is this reaction spontaneous? Anyone? How do we know if it's spontaneous or not? And remember, another word for spontaneous is favorable. Is it going to happen? Is it favorable? I'm like not even seeing a head shake, not even like a small one. Like, don't call on me or acknowledge that I'm shaking my head, but I'm trying to give you.
It's spontaneous, right?
Say that again.
It is spontaneous, right? Because they're both positive.
Okay, Aubrey says it is spontaneous because they're both positive.
I could be wrong. Don't.
Well, yeah, anybody could be wrong. There's times where I'm wrong. That's scary. I better not be wrong. Anybody think it's non-spontaneous? Well, here's the quick way to answer this. We don't have to do any math here. Everybody's like, spontaneous question mark. Let's just go to the table. Remember our dear friend table? Look, if delta G is negative, what does that mean? Reaction is spontaneous. If delta G is positive, guess what? Reaction is not spontaneous.
I looked at the table and I guess I looked at it wrong.
So delta G is positive here. So no, it's not spontaneous. All right, boom, simple. That's how we answer that one. Yep, non-spontaneous. Okay, everybody's changing their answers last second. That's what I meant. Okay, now the second question is, so by the way, to answer that, you just look at the table and you're going to have that for the exam. Does entropy, what is entropy again? Entropy is delta S. Does it increase or decrease? So is delta S positive or negative? How do we know? Remember, entropy is a measure of disorder. That's what we talked about on Tuesday. And what is more inherently disordered, a solid or a gas?
A gas.
Gas. So look at our equation. Say that again.
So entropy increases?
Yes, because we have solids on the reactant side and our arrow is pointing to the gases. These are more disordered. So if we have if we're making more disorder, then entropy is increasing for sure. So it increases. So delta S is positive here. Additionally, another way you could look at that is I have one reactant and I have two products. 2 is more disordered than 1. I learned this the hard way when I added another child to our family. We had 1 child, now we have 2, and there is definitely more disorder in our house. Okay, 2 is more disordered than 1. So you could look at it as number of moles. Third thing, do you expect the reaction to be spontaneous at higher temperatures? This is the hardest question with this problem, and it's not necessarily a straightforward thing. So I need to analyze a few things first. So I'm going to walk you through how to think about these questions. I think you have a couple on your homework that allude to stuff like this and want you to think about this. So I would take notes here and it'll help you on a homework question. Let's analyze what we have so far. I'm going to write out my equation. I know that delta G is positive. That's what we saw over here. And it equals delta H minus T. And I'm going to put brackets because it's times delta S. I also know we just determined that my delta S is positive. Okay. So what is delta H? Can we know anything? We don't have a value given to us, but can we at least know if it's positive or negative? What do y'all think? Is delta H positive or negative here? You got a 50-50 shot.
Could we look at the table and that help us?
The table actually will not directly help you here, but that is a good thought.
Okay.
But you can look, you can actually understand this from a mathematical standpoint. We have a positive answer. Delta G is positive.
Yeah, it would be positive because if you have negative, it'd always be negative, right?
If you just because you have a negative delta H does not always mean your delta G will be negative.
If there's
Sometimes.
if there's one negative and one positive, then it'll be okay. Yeah.
Okay, so think about this. We have two positive numbers in this bracket. A positive times a positive is a positive number. Y'all with me? We also have a minus sign out front. What does that minus sign do to that whole term, T delta S? Makes it
Negative.
negative. Okay, so all of this is going to be negative. All right. Now, if we have a positive answer, it must be because we have a larger positive number right here. For example, if we have 10 minus 1 times 5, look, both of these numbers in the bracket are positive, and this one is also positive, but it's a bigger positive number. Okay, if everything is positive, the only way we can have a positive number over here, if we're subtracting, making this whole term right here negative, okay, that's like saying 10 minus 5, right? 10 minus 5. We only get a positive number on the outcome if this number right here, our delta H, is a larger positive number. It's the only way you get a positive answer, okay? Okay, hopefully I haven't lost you, but all I'm trying to say is delta H is positive here, and that's how we know. So now I want to use this blank slide to explain something. If delta H is positive and delta S is positive, let's go look at the table for just a second. I'm pretty sure what we're going to find sounds pretty redundant. Let's just double check. We're on column or row 3 here. Positive, positive. It's not necessarily certain what delta G will always be. Sometimes delta G could be negative, sometimes it could be positive. And that's what we've realized is, oh, we've got to use the equation. Now, what the question is asking is that we need to actually go back and reread the question. Do you expect the reaction to be spontaneous at higher temperatures? So what we're going to do is a little thought experiment. I'm going to pick some simple whole integer numbers under 10. And we're just going to plug these in, and then we're going to do it once with a low temperature and once with a higher number as a temperature. So I'm going to plug in 10 for H, delta H. I'm going to plug in 1 for temperature, and I'm going to plug in 2 for delta S. Simple whole number integers. What's our delta G here? This equals delta G. What would be your delta G in this case? Both positive. We're playing a scenario where delta H and delta S are both positive. Okay, thank you, Brendan. 8, positive 8. Now let's crank up the temperature. Let's crank the heat up. What number do you guys want to plug in for temperature? I'm going to plug in a 10. Okay, we're going to crank the temperature up times 10. 10 times 2. Now what's my delta G? -10. Thank you. So let's look at this. Go back to question 3. When you have a positive delta H and a positive delta S, if you crank the temperature up high enough, what can happen to your delta G? What did we just see? It went from a positive number to a negative number. Okay. So let's go back up to the table. I want you to make a note. I'm going to draw this right up here. Situations that correspond to row 3, positive H, positive S. Those reactions, when you have a reaction with a positive H and positive S, can tend to become spontaneous or favorable at high temperatures. Okay, so they can become spontaneous. I'm going to abbreviate SP, spontaneous at high temperatures. And guess what? Guess what's directly opposite column or row 4? I keep saying column. Row 4, when you have a situation where your delta H and delta S is negative, we could do the same little number experiment, okay? And if you don't believe me, try one on your own. These will become or tend to become spontaneous, this time at lower temperatures. There are some homework questions that directly ask you. They use the wording like, when you have a favorable delta H and an unfavorable delta S. Let's talk about that for a second, because that can be confusing. Does anybody need me to stay here? Anybody still writing? What does it mean if it says an unfavorable enthalpy? An unfavorable enthalpy. What is an unfavorable? One, enthalpy is delta H. What is an unfavorable delta H? Positive or negative?
Positive.
Yes. A favorable delta H, a favorable enthalpy is negative. So I'm going to go down here. Let's just take note of this for your homework to help you later on. So favorable enthalpy, that is a negative delta H. And then vice versa, unfavorable is positive. And a favorable entropy, which is delta S, that is a positive delta S. Negative delta H, positive delta S always give you negative delta G, but only when they're combined together. But that's why they're called favorable. Questions on that? All right. Are we good to move on? Anybody still writing? Hannah, are you sitting by a window?
Yes.
Like very shimmery glow.
Yeah, there's like rainbows and stuff.
I like it.
It's warm.
Okay. All right. Here's another example problem. We have A breaking down into B and C. And it says that A is a solid, B is a solid, C is a gas. And then it gives us a little picture show here. I think this is honestly straight from your textbook. Here's the key. A are these green spheres. Okay, so this is A, it's a solid. And we can tell it's a solid because of the way the spheres are ordered and arranged, right? Solids have inherently more order this way. B is the faded green. And then C are the gas particles, and that looks like a gas because they're filling the space of the container. They're moving around like gas particles do. It gives us delta H, negative 23.5 kcal per mole. What is the sign on delta S? So how do we answer that? We don't have to do any math here. We just look at the equation. Remember that figure that I showed you guys right above the picture of the deck of cards from Tuesday? There's two ways to analyze this: fewer moles and more moles, and then if you're going from solid to liquid to gas or vice versa. So here I noticed that we have only solid on the reactant side, and on the product side we have a solid and we have a gas. So is delta S positive or negative? Remember, delta S is a measure of disorder.
Positive.
It is positive, okay? Delta S is positive. Disorder is increasing. We are making a gas which is inherently more disordered. All right. Now, considering your sign on delta H, which is negative, and delta S, which is positive, now let's look at the third question. Is the reaction spontaneous at all temperatures, some temperatures, or no temperatures? What do you think? Spontaneous means is delta G going to be negative
It is spontaneous, yeah.
at all, some, or no temps?
All?
All. Aubrey says all. Anybody agree or disagree? If you want to double check, what do we do? Let's just go look at the table. We have a negative delta H, positive delta S. Right there. That corresponds to row 1. Okay, right here. Negative delta H, positive delta S. That will always give you, no matter what the temperature is doing, will always give you a negative delta G. So this one will be spontaneous, like Aubrey said, at all temperatures. Questions on that? Did we even do any math for this? Nope. Did you like it that way?
So I do have one question.
Yes.
What would it look like if they were only spontaneous at some have we done one like that with some temperatures?
Yeah, that's right up here.
When was that one?
This one right here. This one is going to be spontaneous at high temperatures, non-spontaneous at low temperatures.
Okay, yes, yeah. Okay,
Rows
that
3 and 4.
yeah.
Conditions like that are the sum. Okay. And then vice versa. If you have a positive delta H, negative delta S, this is spontaneous at no temps. Okay. You'll never get a negative delta G there. All right. That's the end of delta G for the moment. Okay. So we're going to put a cork in delta G for a minute. But we'll come back to delta G when we talk about equilibrium. So we're now going to talk about the next big topic in chapter 7. So here's the topic so far. Enthalpy was 1, entropy was 1, delta G, and now topic number 4 is reaction rates. So we've been examining this question, how do we know if a reaction will occur? And now we know that delta G tells us directly if a reaction will happen from an energy standpoint, but it doesn't tell us anything about how fast or slow it is. And why does this matter? Well, can anybody think of a reaction that happens but is very, very slow? It doesn't have to deal with like us or the human body or anything, just in nature in general. Rust. Although sometimes I'm like, man, I use this pair of scissors. I'm going to wash it and lay it down the side. And then the next morning I'm like, my scissors have rust on them. So rust can be maybe a little faster than we think. I think of like a landfill. Okay, what is happening in a landfill? Stuff is decomposing. And I mean, maybe one day it'll all be decomposed, but everybody always freaks out that we're going to run out of landfills, right? I feel like that's always like an underlying issue because stuff decomposes very slowly. Okay, so you should always recycle, right? Stuff doesn't degrade fast. We're making things, everybody that's talking about sustainability these days, we're making and using products at a faster rate than we can resupply them, right? Because decomposition is a very, very slow reaction. Can anybody on the flip side think of a reaction that happens very, very fast? We're all going to do one right now. I want everybody to take a big breath in. And now let it out. Do you feel better? Okay, what reaction just happened? You just did a reaction, your body did. Just, okay, breathing. Think about what's happening though. In a split second, our bodies have to bind oxygen and release CO2. And that has to happen very quickly and very accurately, right? And that's just one reaction of many, 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 okay? Yeah, respiration. So it matters how fast things happen is what I'm trying to say. It matters. It matters how quickly we digest our food, right? It would do our bodies no good if we eat all this food, but then we can't digest it in time for our cells and our tissues and our things to get the nutrients, extract the nutrients from that food. So that whole process of breaking food down, distributing it to our cells and our tissues has to be very efficient, very fast. So how can we learn in a helpful way something about reaction rates that will benefit us? Well, let's just look at the idea of rate or speed of reaction. How do we determine the rate or speed of a reaction? It is by efficient collisions. All right, and what is an efficient collision? Okay, for a reaction to happen, we know molecules have to collide, but they can't just randomly collide. All right, molecules collide all the time. Unfortunately, things don't react with us. Okay, the colliding of two molecules, it has to happen. It has to have two things for a collision to be efficient and a reaction to take place. Number one, you have to have the correct orientation. And number two, you have to have sufficient energy. So you have to have the correct orientation, you have to have sufficient energy, then you can get a reaction. An example is down here. This is a picture from your textbook. Anybody ever heard somebody freaking out about the ozone layer? Okay, what's gonna happen to our ozone layer? Glad we don't live in the 80s where everybody thought our ozone layer was gonna go away forever because of hairspray. Okay, ozone is a molecule O3. Here it is right here. And here's another molecule in our atmosphere, nitrogen monoxide, NO. And when these two react, they do all the time in the atmosphere. The only way that you get a reaction is if the nitrogen is the one that collides with the ozone molecule. Okay, so here we have this blue nitrogen atom. When it collides with ozone, here they are colliding. What happens is this terminal oxygen molecule or atom from the ozone is going to go away, and it's going to break off from ozone, and it's going to combine with the NO. And now you have oxygen, which is good. We need more of that. And we have NO2. And that's how the ozone layer breaks down. One example. Okay, but if those two molecules collide, it's just that the oxygen atom is the one that hits ozone, you're not going to get a reaction. And I know this seems very, very technical and like who cares and whatever, but this is one way that we can appreciate chemical reactions, honestly, the complexity of it. Okay, things have to collide the proper way. So that's an example of correct orientation. Sufficient energy, to kind of intro a talk on how we have sufficient energy, we need to actually draw something called a reaction diagram. So we're going to take a second and draw a very generalized reaction diagram. I want you to know how to draw these for the exam. Okay, any reaction diagram, let's just draw, it's a reaction on a graph. Okay, that's what a reaction diagram is. It's going to be a graph that we're going to draw. They all have the same X and Y axis. I actually want to do this in black. So draw a little graph on your paper, X and Y axis. On the X axis, you're going to put reaction progress. As you go from left to right, the reaction is progressing from reactants to products. And on the Y axis, you're going to have delta G. Okay, or you're going to have free energy. Okay, so that is the amount, that's the change in energy as the reaction goes. So that's always, for every reaction diagram, you need to label your axes properly. Another thing that is always on every reaction diagram is an energy level that corresponds to how much energy is locked up within the bonds of the reactants. So let's just arbitrarily say this is how much energy our reactants have. And I'm going to put a little R underneath it to indicate reactants. Okay, so every reaction diagram has the amount of energy associated with the reactants marked off. And it also has the amount of energy associated with the products. Let's just say the products have this amount of energy. I'm just making up numbers here. Now, for a reaction to occur and go from reactants to products, they have to clear what we call the energy barrier. So I'm going to draw a peak. All right, let's just say, and it's going to start with the energy level of the reactants because that's our starting point. And it always goes up. You have to clear this peak, okay? So we're going to just draw a peak like that. And then it's going to end. You're just going to then go connect it to your energy level of your products. Once you clear that peak, you're just going to keep going until you've made your products. Okay? So this is an example. Not every reaction pathway looks like this, but this is just an example of a reaction diagram. So another couple things that we can point out here. The difference, think about this, the difference between the energy level of the reactants and the energy level of the products, if we just extended these lines over one another, guess what that is? As you go from reactants toward your products, you're decreasing in energy, right? You're becoming more stable. This right here is your delta G, okay? Because delta G is the y-axis, so your change along the y-axis, that is your delta G. Now, what can you say for this reaction? Is delta G positive or negative? Is your change in energy as you go from reactants products positive or negative?
It looks like it's decreasing. So negative.
This number called me earlier today. That's annoying. Sorry, everyone. Okay, whoever just said something, I think you said the right thing. I think you said it's negative.
Yes.
Yes, that's correct. So this is a negative delta G. So this is a favorable reaction, right? This is is it an exergonic or an endergonic reaction? Anybody remember those terms, exergonic or endergonic?
Is it exergonic?
Exergonic, yep. Don't confuse exergonic and exothermic. Exothermic is negative delta H, exergonic is negative delta G. All right, now I'm going to draw another reaction pathway. I'm going to do it in a different color. Let's say we have another reaction and we're starting out with this amount of energy for the reactants. We'll just keep that the same. But let's say this time our products have this amount of energy. What would a reaction pathway for that look like? Well, you're still going to have an energy barrier. So we're going to, but we're going to have to come up even higher than the level of the products, okay? So we're still going to have an energy barrier, and then we can come down and make our products. All right, so that's another example of a reaction pathway. Now let's mark off the delta G for this one. Start with the energy level of the reactants, extend the line from the energy level of the products. That change from that line to that line, that is your delta G for this reaction. Now, what can you comment or say about this reaction? Is it favorable or unfavorable? Delta G here is positive, and we know that is unfavorable. We said this one down here was favorable. All right, so I just wanted you to get some practice real quick of drawing and recognizing the basic things about a reaction pathway. Now, the whole sufficient energy thing that we're talking about up here to produce a reaction, that is marked off by what we call activation energy. So I'm going to scroll down to the next slide. We're talking about activation energy. We abbreviate activation energy as E for energy, ACT, subscript ACT for activation. Activation energy. All right. This is the energy required to begin the reaction. And this is actually marked off on the graph when you go up to that energy peak or that energy barrier. And it is determined by how efficiently molecules collide. If you get just the perfect proper orientation, then molecules are set up that when they collide, the amount of energy they collide with can make the reaction go. Another important thing to know about activation energy is right here. It determines the rate of the reaction. It determines how fast the reaction will go. So if you have a reaction with a very small activation energy, guess what? That's going to be a very fast reaction. If you have a reaction with a very large activation energy, that's going to be a very slow reaction. Okay. So I want you to look at these three graphs. We actually have three drawn on this slide. I want to know which one, A, B, or C, looks like the fastest. I actually haven't told you what activation energy is, though. Every single one of these has activation energy marked off. And it is, for example, A, if you start at the energy level of the reactants and then you extend the line to the peak of the energy barrier, the peak part of your graph, that change right there from reactants to the peak, that is the activation energy for any reaction pathway. So if we go up here, reactants to the peak, That's the activation energy for that one. And then same for the one in blue that we drew. Here was the energy level of the reactants up to the peak. This change right here, this big line down to the blue one, that is the energy, activation energy for that reaction as well. So that's how you mark off and examine. I'll stay right here for a second. Y'all are still drawing. That's how you label the activation energy. So we're going to go back down to A, B, and C on the next slide. Which one is the fastest?
C.
Yes. How do you know? It has the smallest activation energy. It's this teeny tiny one. All right, that is the activation energy. And it's marked off over here for you as well. All right, now, so this one is the fastest. Which one looks like it would be the slowest?
B.
B. B has the largest activation energy. It's like almost the whole graph, top to bottom. So this one definitely, A, the activation energy is only about half the graph. So this one is definitely the slowest. Okay, so these are the kinds of things I want you to do. Talking about reaction rates, which we're not done, we're almost done. I want you to be able to, one, draw out an energy diagram or reaction diagram, label the reactants and products, draw your delta G, draw your activation energy, and then make a comment. Is this going to be a fast reaction or a slow reaction? Okay, things like that. Is this a favorable reaction or an unfavorable reaction? Okay, questions on how we just did that kind of stuff?
So the faster the reaction, the more favorable it is.
Not necessarily. And that actually, I'm glad you just said that. Is that Ashlyn? It sounds like Ashlyn.
Yes, it is.
I want to read, I forgot to read this line right here. So I'm glad you just said that. Activation energy has zero impact on the sign or the size of delta G. Delta G determines if it's favorable or not, if delta G is positive or negative. The activation energy just determines how fast it will happen. These are apples and oranges. So whether you have a fast reaction, that does not necessarily always mean a favorable reaction. You can have a very fast reaction, but it not be favorable. Does that make sense? You can have a very slow reaction that is favorable, on the other hand. All right. Now, fortunately, we have found ways to manipulate reaction rates. Okay, in a chemistry lab, in a research lab, you know, you have whole rooms that are like refrigerator rooms, cooler rooms. I remember in grad school, fortunately, I never had to do this, but there were people who had to do their reactions and their research in what we call the cold room. So they literally have to spend all day in this cold room doing their reaction because they want to do it at a certain temperature, because temperature has a huge effect on reaction rates. So that's actually the first thing we're going to write down here. We can change reaction rates. The first property we use to do that is with temperature. And if you increase temp, you are going to increase the reaction rate. It'll go faster. And if you decrease temp, you will decrease the reaction rate. It'll go slower. Okay. So let's actually look at this figure I have just down below. We said if we increase temperature right here in this blue square, how does this increase the rate of the reaction? Well, reactions are just the collisions of atoms and molecules, right? That's what's happening. And when you increase the temperature, you are increasing the energy that those molecules contain. So if something has more energy, it can move faster. Does that make sense? And if you are doing a reaction in a confined space, if you have a box or a container and it has an X amount of volume and you are doing a reaction in that container, the faster the molecules move, the more often they will collide. Okay? So what's going to happen if you increase the temperature, you're going to increase the frequency of collisions, okay, between your reactants. And if they're colliding more often, you're giving them the chance to react more often, and your reaction rate will increase. The more often that they will collide properly, and you get a reaction. Also, you're increasing the forcefulness of the collision. And if they are increasing more forcefully, then we're giving those atoms and those molecules a better chance of having sufficient energy and clearing the activation energy barrier so that they can then proceed with the reaction pathway and make the products. So that's two ways. Temperature can do two things. All right. The second property, any questions on that? All right, the second property is by changing, and I'll say change in concentration. All right, what do I mean by that? Changing the concentration of the reactants, of your reactant molecules. I'll put of reactants. I'm gonna shrink this down. Don't you wish you could do that to your paper sometimes? Does it make you mad when I can do that to my screen? You can't do it to your paper. Sorry. All right. So that's one. We'll look at that in just a second. I'm going to go ahead and write the third one in as well. Catalyst. The third way we can change a reaction rate is with a catalyst. Has anybody ever heard this word before, a catalyst? There's a very biology-ish term we use for the word catalyst. Anybody know what it is? Catalyst, and yes, thank you, Zoe. It's an enzyme. Okay, so enzymes are proteins. Your body has roughly 60,000 proteins. Does that not impress you? 60,000. And not all of them act as enzymes, but many of them do. So if you've ever studied metabolism of glucose, okay, breakdown of glucose, that whole reaction, it's like 8 or 10 reactions, only happens because every step is happens because of an enzyme, okay, a catalyst, making that step happen and happen very quickly. So let's go back to number 2 though. How does a change in concentration affect the rate of the reaction? If we increase the concentration, and what do I mean by concentration? We're actually going to define this in a little bit, but what do y'all think I mean when I say the word concentration? It's a very chemistry oriented word. Anybody know or have a guess? No? Dilution, okay. Something that's diluted is not very concentrated. So Brendan, dilution is all over the word concentration. I don't know if it defines it, but it is a type of concentration, okay. How dense something is, Zoe, that's a really good guess. But essentially it's how many molecules of something you have per volume of whatever solution or mixture you're talking about, okay. Anybody ever had, well, actually, I'll save this question for later. It brought up good conversation when we actually get to defining it later. But if we increase the concentration of our reactant molecules, we are going to increase, again, the frequency of collisions between our molecules, giving them the chance to collide and react if they collide properly. Vice versa, if we decrease the concentration of our reactant molecules, we're going to decrease the frequency of collisions and therefore decrease the rate of the reaction. Okay, lastly, let's talk about a catalyst. It is a substance that increases the rate of a reaction, but itself it is not altered in the reaction. We cannot think of a catalyst as a reactant. It's not a reactant. The way we write in catalysts, let's say you have a reaction A plus B makes C plus D. You would write in catalyst right over this little arrow. You would say, here's my catalyst. It is part of the process of what you're going to do to the reactants, but it is not a reactant. Okay, it's not altered in the reaction. A and B, our reactants, we know are going to be altered. They're going to break bonds. They're going to trade atoms. Something's going to happen. But how does it speed up the rate? Well, essentially what it's doing, if we think about our reaction diagrams, is a catalyst lowers the activation energy. And here's how it does it. 3 ways it does that. It creates a different reaction pathway. We're going to draw an example in a second. It will fix the molecules in proper orientation. My favorite analogy for this is anybody have siblings that you get in fights growing up, and your mom or your dad would be like, okay, y'all hold hands and kiss. You'd make them come together in the right way. That's what a catalyst does. Okay. It fixes molecules, it brings them together, and it forces them to join together in the right way. And then that kind of also alludes to part 3. Sometimes it brings them together and it lets them bump into each other, and sometimes it just fixes them right in the perfect orientation together. Okay. So let's draw a picture though of a reaction pathway without a catalyst and then with a catalyst, and see how they're different. So we know if we have some energy level reactants, and we'll just say some energy level for products, we know that we're going to have a reaction barrier. Okay. And then once we clear that, we're just going to go on down and make our products. So let's mark off the activation energy. The top of the peak down to the energy level of the reactants. That is the activation energy for this reaction. And this reaction is with no catalyst. Now let's draw a reaction pathway with a catalyst. If it lowers the activation energy, it does not change delta G, remember? So we have to have the same energy level of our reactants and products. The only thing it's going to do is it's going to make that peak a little bit lower. So go ahead, I want you to try to draw it. Try to draw what you think I'm about to draw. Draw the same pathway, but with a lower activation energy. You still have to have an activation energy, but just not as high. So you should have something kind of like this. Okay. So here, we now draw our activation energy. It's about half the amount. And this one is with a catalyst. All right, any questions on a catalyst or how we can manipulate reaction rates?
I have a question.
Yes, Sarah.
I didn't have I have the PowerPoint on here, but I didn't have the blank thing. I don't know if you can see, but I have like the actual like.
Yeah,
in there.
that's the
Is there-
unaltered one.
Yeah, is there a reason that there's 2 humps when the catalyst is present?
Sometimes catalysts can be a little more complex than just what I'm drawing. And sometimes you can have different kinds of, what's the word for, I'm blanking right now. They call it the activation site. And sometimes when a reaction happens, you can have multiple like orientations that the molecules have to hit before they make the products. So if there's multiple orientations that they have to hit and collide multiple ways before you get your products, I'm explaining it to you as though they just collide once and then it's done. And sometimes it's more complicated than that. So sometimes there can be a little dip in there and you get little 2 bumps because there can be more than one activation or site. I don't know if that helps, but essentially they'll have to bump together multiple ways before you get your products. And each one of those little orientations has their own activation energy. And that's why there's 2 little bumps there, but we're not getting into that in that amount of depth. That would be more straight like a biochemistry class. Does that help, Sarah?
Yes, that helps. I was just curious.
Yeah, no worries there. I deleted that so we could draw on so I could simplify it for us. But the same idea. Okay, so that's it for reaction rates. We're actually done talking about reaction rates. So I want you to know from this big main umbrella topic, reaction rates, I want you to know how to draw an energy diagram. And I want you to know how to explain the different ways we can alter rates, how we could increase a reaction rate, how we could decrease a reaction rate. Okay. And if you choose to tell me how a catalyst does it, be able to explain the different ways that a catalyst would alter the rate. Questions so far? Okay. We've got about 20 minutes left. So we're about to get into equilibrium. We're not going to finish equilibrium. We're going to get most of the way through it. And whatever we don't finish, I'll do on a little video plus Le Chatelier's principle. And I'll upload those videos by tonight or tomorrow morning. But equilibrium is quite a big topic. And I will tell you, it's not one of my most favorite topics. Okay. But it is a very important topic. And this is going to feel very, very brand new. So it might seem kind of really, really confusing at first. But then hopefully we may not get to it today, but in the videos at least, if you work along with it, we're going to work some problems and hopefully it will kind of all shake out and make sense by the end of that. So before I just define what equilibrium is, I want to bring delta G back into our conversation. So we have talked about how delta G, a positive or a negative delta G, means a favorable or an unfavorable reaction. We've been hammering the sign of delta G, positive or negative. Well, I'm going to throw you a curveball. You ready for the curveball? What if delta G is 0? What if it's not positive or negative? You're like, I don't know. I didn't know that could happen. What does that mean? Well, what would it look like on an energy diagram if our delta G was 0? Remember, delta G, if we go back up here, I have to go up further than I thought. Delta G is the level between the reactants and the products. So what if delta G is 0? What if there's not a delta G because it's 0?
It would just be a straight line.
Straight line. You still have to have an activation energy.
Would
But
it be
essentially, go ahead, Hannah, or whoever.
it was me. Like the straight line, maybe a little hump, and then a straight line.
Like
Okay.
back to the same level.
Yeah, y'all are exactly right. So you'd have your energy level of your reactants and the energy level of the products would be about the same. And you would still have a little activation energy, but the energy level of the products is no different. So now let me ask this question. Is it favorable? Is this reaction favorable to take your reactants and make your products from an energy standpoint? Is it any more effective or are your products any more stable than your reactants?
Don't you always want to be at equilibrium? Or if this is like a reaction in our body, wouldn't it always want to be?
Any system that can reach an equilibrium, yes, it will. It will. So yeah, equilibrium is a good thing. I don't want it to sound like a bad thing. But going back to this question, is this kind of a reaction? Let's say you have A and B are your reactants and you're making C and D as your products. If delta G is 0, can you say that it's favorable to make your products from an energy standpoint? It's not any more favorable than the reverse of that. What do I mean by that? A and B will collide and make C and D. Okay, reactions are going to happen because molecules are always moving. So A and B will collide, give you your products. But what will also happen when you have this situation, because it's not energetically more favorable, if A and B mix, here's what I just said, they'll produce C and D. But what will also then happen is C and D, once they are made, they can form efficient collisions too. They can react and make A and B. Whoa, didn't know that could happen, right?
So it just goes back and forth. They can just keep.
Yeah. Yep. Did I just blow your mind? I don't see any of those exploding brain emojis. That's what I would be using right now. This is called, what do we call this? A reversible. In the morning lecture, that you can give little emoji signs, right? Okay. I feel like I'm a preacher asking for an amen. Amen. There you go. All right. So we have a reversible reaction. When you have that, the forward reaction is the initial one where you have A and B make C, D. We would now call this the forward reaction. Okay. And then when you take your reactants and you're remaking your products, we call this the reverse reaction. Okay. So now we have a forward because energetically it's not more favorable to go one way or the other. So both are going to happen. All right. Now to combine this, the shorthand notation to make it more simple is we're just going to say A plus B. We're going to do a little half arrow forward and a half arrow back. Make C plus D. You've probably seen pictures like this in textbooks or different things where you have a reversible arrow. And we call this this is the reversible reaction. Okay. So I know I still have not defined equilibrium yet, but only systems that are reversible can reach equilibrium. Okay. You do still have reactions in nature that are one direction and one direction only. Okay. I'm trying to think of a good example of that. Like once you take like I don't know, this is a silly example, but if you have a mirror and you shatter that mirror, obviously that's a one direction sort of reaction. Okay. We can't necessarily we can piece that mirror back together, but that's not the same mirror. Okay. You still have reactions like that in nature where they're just one direction only, but those cannot reach equilibrium. It's only systems that are reversible that can reach what we call equilibrium. So let's further our understanding of reversible reactions so that we can define what equilibrium is exactly. Now, I introduced this slide. I said, what if delta G is 0? And to actually let you in on a little secret, delta G can never actually be 0.000, but it can be very, very close. Okay. But you'll notice that in usually one direction or the other, something is a tiny bit more favorable. Okay. Whichever one ends up being a tiny bit more favorable, we consider that direction, the making of those things, the forward reaction. So here you see that the level of C and D is slightly lower than A and B. Okay, so the forward reaction here would be the A plus the B make the C and the D. That would be forward. But if you look at the reaction down below, A and B are more stable. They have a lower amount of energy. So the forward reaction here would be that C plus D make A plus B. That would be considered forward. That's the way nature's going to want to tend to go. Okay. So we say the more favorable reaction, the making of the things that are lower in energy, we write that as the forward reaction. Now, whatever we write as forward, whatever we write as backwards or reverse, eventually the rates of those things are going to level out and equal out. And now we're getting into a state of equilibrium. And that's all this bullet point is saying. I'm sorry about this slide. I hate slides like this that are just a bunch of text. But unfortunately, with equilibrium, there's kind of no way around it. And I didn't want you to feel like you have to write all this down. Eventually, the rate of the forward and the reverse reactions will be the same. And at this point, the concentrations of the products and the reactants are not changing. When you're doing reactions, but you're not changing the concentrations anymore of your reactants or products, you have reached a state of equilibrium. I'm going to say that again. Both the forward and reverse reactions are still occurring. People tend to think equilibrium is this very static, boring state. It's a very dynamic state. You have double reactions happening, okay? But because they occur at the same rate, we are not changing concentration of our reactants and products. Okay, this is called equilibrium. I'm going to give you an example. If you want the actual technical definition, it's here on this slide. State where forward and reverse reactions occur at the same rate. So there is no net change in product or reaction. Oh, still writing. Haley, what do I need to go back to? Do I need to go back to anything? Do I just need to slow down? You guys hanging on? Do I need to slow? Am I moving too fast? Okay. I'm going to give you an analogy for understanding a little too fast. Okay. I'll pause for a second. Anybody who's still writing, catch up. To introduce this analogy, though, we'll talk about escalators. Anybody seen the movie Buddy or Elf? Buddy the Elf. I always love the escalator scene. Oh, it's almost Christmas time. Anybody start listening to Christmas music before Thanksgiving? Uh-oh, this is a very controversial topic. I do. My husband does not. So it kind of is war in our house. Literally, it's like, I don't know, I'm trying to think of a scene where you're like changing the radio stations as though there are buttons anymore. But yes, I do. Okay, Christmas music is very good, and I think it is very sad to limit it to just 1 month of the year. So I like to listen to it for 2 months of the year. I'm sorry. Anyways, back to escalators and equilibrium. Let's look at this picture here. This is a picture. Guess what this is a picture of? It looks like it's a picture of a mall. I guarantee you in 20 years, I could show this picture to like my grandchildren. They're going to be like, what is that? Okay, anybody think malls are going to go out in like 20, 30 years? I don't think they're going to be a thing anymore. I really
Could
don't.
be.
What?
I said could be because so many people shop online, but then
I
there's also
know.
a lot of people who do like the atmosphere and like to go shop. So I don't know.
That's true. You have like your outlet malls. I'm a fan of those, but I do a lot of shopping online. Okay.
Yeah. But then it's like a tourist thing too, where it's like that's like a thing to do. So that is kind of a tourist attraction too for some people.
I know.
Be able to go out.
I think malls are going to become a thing of the past. So that's my opinion. It's my personal opinion. We'll see if that happens or not. All right, let's say we're at a mall though, and let's say on floor 2, there's, I don't know, 500 people. So there's 500 people up on floor 2, and let's say on floor 1, there's like 250 people. Okay, I'm just making up numbers. We know on escalators, what do you know about escalators? Let's say this one is the downward escalator, and let's say this one is the upward escalator. We know escalators move at the same speed, right? So if someone from the second floor were to step on, here's person number 1, and they step on the downward escalator, at the exact same time someone from floor 1 steps on the escalator. Anybody used to step on and then try to see how far you could get your legs to spread out before you actually step on the other one? And then you trip and fall. But if they step on at the exact same time, we know what? They're going to reach the opposite floor at the exact same time, right? Because those escalators are supposed to be moving at the same speed. Okay, so that's kind of like equilibrium. Does that mean that we have the same number of people on floor 2 as floor 1? No. And let's even make this even more chemistry on it. If these are our reactants and these are our products, what equilibrium is saying is that the concentration, the number of reactants and the number of products at equilibrium, they're not necessarily going to be the same. Sure, so you can have a reaction where the concentrations are roughly equal, but for most reactions, you might have more products at equilibrium or you might have more reactants. Either way, all it means is that you are making the reactants and the products at the same speed. You are sending people to the opposite floor at the same speed, okay? And that's kind of what all these exclamation marks and this angry statement is getting at, okay? Now, if you are still way out in left field about equilibrium and what it means, I put this, anybody ever use TED Ed, little TED Talks? Anybody a fan of TED Talks? I put this little link down here. There's a short TED Ed YouTube video. I encourage you to go watch it. It's kind of another silly analogy, like the escalators thing. It's not necessarily, but sometimes I think when we pull our head out of chemistry world and we actually talk about chemistry using real world examples or silly examples, it can help us understand. So if you want to go watch that video, I encourage you to just copy and paste that link and check out that video. It'll kind of walk you through equilibrium as well. Questions on equilibrium so far? All right, we're getting near the end, but I need to explain one more thing. I've been using the word concentration. Okay, the concentration of the reactants and the products are not the same. They're different, blah, blah, blah. But what does concentration mean? Now, you nursing people, y'all need to listen up because you're going to be using this stuff a lot. You're going to know you need to know how to calculate this and how to communicate this. I'm going to enter the slide right down here. What does concentration mean? Well, there's multiple ways we can communicate and measure concentration, but all it essentially is an amount of, I'm going to use this word we've not used before, solute, per a volume of solution. And it's an amount of solute per volume of solution. Now, what is solute? In any solution, you have something being dissolved and you have a liquid, usually it's a liquid, that is dissolving your particles, okay? Say you have salt and you put it in some warm water and you stir it up, you're dissolving the salt in the water. The salt is the solute and the water is the solvent. And together they are the solution. Anybody make Country Time? Country Time's the best, right? Country Time is way better than Kool-Aid, right? Well, if you're making lemonade, that powder that you start out with, the Country Time powder, that would be like your solute. And you dissolve it in water and together you have a solution of lemonade, okay? Anybody ever had really bad lemonade before? You take a drink and it's like disgusting because it tastes like just weird water. We would call that a dilute solution. On the flip side, anybody have it and it's like disgusting because it's way too gross? It's just way too sugary. In the first lecture, somebody goes, diabetes. Yeah, it's too concentrated. Okay, there's too much solute. All right, so that's just a little bit of an example of how to understand concentration. So your solute, I meant to write, is the dissolved particles. And the solution is the solvent plus the solute, all right, together. We're going to come back to this in chapter 9, but I just wanted to introduce it right here. Now, there's 2 ways that we can communicate concentration, and there's probably even more ways than this. When my sister makes sweet tea, we call it diabetes in a cup. I can't drink it that sweet, but I also don't like sweet tea, but I don't like it that sweet. Okay, one way is weight volume percent. Weight volume percent. What that is, it's the grams of solute, because gram is an amount, per milliliter of solution. And you multiply it by 100 to turn it into a percent. You can also use something called molarity. And this is what we're going to use when we talk about equilibrium. Molarity, we abbreviate with an M, and it's the moles of solute, the dissolved stuff, per liter of solution. Okay. So it's just an amount of solute per volume of solution. And we just use different units sometimes, grams or moles, milliliters or liters. Okay, questions on that? All right, well, we really are pretty much at the end of our time. I don't want to get into this next topic because we're going to have to just stop in the middle of it. But I've kind of left you on a big cliff edge, I know. And so I will video the rest of this equilibrium constant and then how to calculate